We're going to get started with the next section of our in-depth data analysis talks. We're going to have two more talks, kind of mirroring the first two, first by Dr. Julia Correa. Julia is a research scientist at Lawrence Berkeley National Lab in the Energy Geosciences Division. She got her PhD from Curtin University in Australia in 2019, focused in DAS for seismic imaging and reservoir monitoring of CO2 carbon sequestration. And this is going to be a talk really focused on continuous time-lapse monitoring, which is a very interesting application, kind of looking more towards this kind of large time kind of aspect and kind of real-time monitoring side of DAS. So with that, looking forward to it. Julia, take it away.
Thanks, Nate. Hello, everyone. Really excited to give this presentation here. So, yeah, like they said, today this presentation will be about how to use DAS for permanent monitoring applied to carbon capture storage projects. And here I'll be showing two different project examples. So we use DAS as part of the monitoring program. And by the end of this presentation, I hope that you have a good understanding of how we can use DAS for permanent monitoring, the different data sets that we can acquire with DAS, how we can, the different ways that we can deploy fiber, and what are the advantages and limitations of using DAS for permanent monitoring. So before I continue, I just need to, I have to acknowledge all the contributors. This is a long list of people who have worked in these two different projects. And I can go forward without acknowledging that, and especially acknowledging the contribution from Roman Pevsner, who's the lead in the, of the geophysics part in the Otway project. Barry Freisfield, Tom Daly, Michelle Robertson, Todd Wood, Scott McDonald, who's part of the ADM ICCS project, and also Jonathan Franklin. So for those who are not so familiar with carbon geosequestration, I'll take it back a little bit. So carbon dioxide geosequestration is the process of capturing and storing carbon dioxide, which is one of the main greenhouse gases, into geological formations. So when you store the CO2 in subsurface, you need to make sure that the stored CO2 is safely down there for a really long time, that it's trapped, that's not escaping, it's not leaking, and that it has a predicted behavior. So there are different ways that you can monitor a long time that the CO2 is safely trapped in there, but one of the main methods that you use for monitoring, for long-term monitoring, is time-lapse seismic. So the acquisition of several data sets or several seismic surveys over time. And because you can capture a long time any changes in the seismic signal that are related to the injection of the CO2. So actually, a fun fact, there is a new tax benefit implemented, well, relatively new, implemented in the United States in 2018, which is called the 45Q tax benefit, that is meant to give incentives for CO2 geosequestration. So one of the requirements that you need to have to be able to get this tax incentive is to demonstrate that the injected CO2 is in subsurface, and demonstrate this for a really long time, for decades. I actually don't know how long you need to be able to demonstrate for this 45Q. I think it's 30 years. If someone has this information, you can put that in the chat, but I think it's 30 years. But my point is that seismic monitoring is really important. But when it comes to CO2 geosequestration, it is especially important because you need to demonstrate that the injected CO2 is there for decades. So the conventional way that you acquire 4D seismic, time-lapse seismic, is that you use these huge fiber-sized sources and you use thousands and thousands of geophone receivers. And you need a lot of people to deploy this equipment, a lot of people to operate this. And usually these type of surveys, they are really expensive. And because they're expensive, it takes, people usually acquire them every 2 years, 3 years, 4 years, sometimes every 5 years. So this ends up giving a very sparse temporal resolution for us. And because you come back 2 years later, there's a building in the place where you previously had a geophone. So you can't really repeat the exact same position. So it gives a relatively poor repeatability. So what can DAS help us in here? Well, DAS, it can use fiber optic cables, right? Fiber optic cables, we can deploy them permanently. They last a really, really long time if you deploy them permanently. And because they can be deployed permanently, they end up being cost effective in the long term. And we are able to acquire fine spatial sampling with the DAS data, a lot finer than what we usually get with the geophone. And because the fiber is installed permanently, we are able to have on-demand acquisition. So we don't have to wait 2 years or 5 years anymore. We can just acquire data anytime. So in this presentation, I will show you some of the results of 2 different CCS projects. The first one that I'll talk about is the CO2 taxi Otway project in Australia. And the second one is the ADM ICCS project in Decatur, Illinois. So the Otway project is Australia's first demonstration of deep geological storage of carbon dioxide. It actually is in its 3rd stage of operation. So this is the demonstration project. It isn't commercial. So we inject small amounts of CO2 into sedimentary reservoirs at 1,500 meters deep. So in the previous 2 stages, we had deployed about 40 kilometers of fiber optic cables, and the idea was to test that against conventional techniques and see if we could be able to use that as one of the main receivers for the next stage. So now currently we are in stage 3, and the main objective of stage 3 is to develop a continuous on-demand monitoring of the CO2 storage by using remotely operated techniques. So for this, in this stage, they are mostly relying on using DAS, because DAS can be remotely operated, can be installed permanently, and also they're relying on using a range of permanent sources. So along the 3 stages of the project, we have deployed, as I said, and acquired a variety of different data sets with DAS. So up until the stage 3, we deployed about 40 kilometers of fiber optic cables on the surface. So we dug a trench, and this is how we would deploy the fiber optic cable. And we acquire a range of seismic data from 3D surface seismic to 3D VSP, offset VSP. And we used also a range of different fiber optic cables. So we had conventional telecom fibers. We had engineered fibers made to improve the DAS sensitivity. And we had this helically wound fiber made to improve the angle sensitivity of the fiber. And we're going to go a little bit over that in a bit. So as a preparation for the stage 3, we wanted to test the performance of DAS, offset VSP against conventional techniques like geophones. And in this trial here, we had just deployed our first permanent installation of fiber optic in the well. And in this cable, we had 2 different fibers. We had the standard fiber, which is a telecom fiber, and we had a second fiber, which was designed specifically for seismic surveys because it improves the backscatter of the light backscatter. So it gives you a more sensitive measurement, if I could say that. So in this test, we wanted to basically see how the offset VSP acquired with that, with these two fibers, would relate to a conventional sensor like geophone. So this is the zero offset VSP shot until the furthest offset, and this is at about 2 kilometers far from the well, where the source is 2 kilometers far from the well. Here we're using Silixa interrogators, and in this case, this is a fiber-side source. So you can see that from just looking at the VSP data acquired with both fibers and the geophone, you can notice that the fibers are able to record reflections quite well, and even smoother than the geophones, because the geophones here, you can get very fine spatial samples. They are deployed in the well at every 15 meters. So you can see that the geophone is actually a little bit aliased in some of these reflections. And but also when we compare the two different fibers, we see that the engineered fiber has slightly lower noise floor than the telecom fiber. We calculated the signal-to-noise ratio, and we can see that, for example, this shot point, which is about 50 meters from the well, the geophone data gives about 40 dB signal-to-noise ratio. The telecom fiber gives about 25 dB signal-to-noise ratio, and the engineered fiber actually it gives a very similar quality to the XPC geophone. One thing that I want to point out is that look at the far offset. Look how we can see the first arrival in the geophone, but when it comes to the DAS, the first arrival is basically not there. This is related to the angle sensitivity of the DAS. And this is important because if you're planning a survey with DAS, you have to account for how far you can go, how far you can put your sources, your signals, so you're able to see the reflections that you want. Right. So as we saw before with Nate's presentation and how we have been discussing these past 2 days, we saw that the amplitudes of the P waves decay is cosine square of the angle of incidence. And this is exactly what we see for both these fibers. Right. So the stage 3, as I mentioned before, it relies on the use of gas in several wells. Actually, there are 6 wells with installation of gas. They are going to be used as a primary sensor for the monitoring, actually. And one of these wells, which was the first well where we installed gas, so the first installation was actually a tubing installation. It was a semi-permanent installation. The other 5 wells that we installed later on were permanent installations. So the fiber was cemented behind casing. So here, we just wanted to see how the installation of the fiber itself varies the signal qualities, varies the signal-to-noise ratio. So we applied the 3G VSP with both cemented fiber and on-tubing fiber. So this is just a little drawing to illustrate the 3 different ways that you can deploy fiber in the well. So you can basically deploy with retrievable way, which is inside the tubing. In one of the cases where we applied 3G VSP, it was deployed attached to the tubing, and the other 5 wells that we have, the permanent installation, is cemented behind the casing. So we calculated signal-to-noise ratio for each shot point for the cemented fiber and the on-tubing fiber. And just by looking at them, you can see the cemented fiber gives a lot higher signal-to-noise ratio than the on-tubing fiber. Actually, if we do a difference, the improvement in signal-to-noise ratio is of about 10 to 15 dB if you cement the fiber. So if you're planning a gas survey in the well, the first option should be cementing the fiber because it has a better coupling. So the stage 3, again, it's the main objective here is to build this continuous on-demand acquisition and processing, so you can get an image of the movement of the CO2 every day. And the main sensor for this stage in Otway are gas. So gas installed in 6 wells, 5 permanent installations. And we have also these permanent sources. We have 9 permanent sources that are surrounding where the predicted plume is. And these permanent sources are called surface orbital vibrators. They're developed in LBNL. And so the idea here is that we have these 2 equipments that are completely remotely operated. They don't need a lot of people to operate them. They give you, you can retrieve the data from outside the site, so remotely. And we're building now this automated processing flow. So every day you can just see how the development of the plume is happening in subsurface. So we've tested these 2 equipment, so the gas with the surface orbital vibrator, various times. So this field trial was accepted now for publication, so you can see that soon. We have newer field trials that now I've submitted recently and it's under review. But the idea here is that we want to see how good is the quality of the gas and SOV data. And also we trial that using single mode fiber and engineered fiber. This engineered fiber is called Constellation, which is an engineered fiber from Silixa, but there are a lot of different versions of engineered fiber out there in the market. And we can see that, again, the engineered fiber improves the signal-to-noise ratio of about 15 dB. And if we look at the frequency spectrum and compare that, the frequency spectrum of the single-mode fiber with the engineered fiber, you see that for the sweep range, it's very similar, right, as it should be. But the main difference between these 2 fibers is in the noise floor. So you have a huge drop in the noise floor when you use the engineered fiber. And we processed these 2 data sets using conventional VSP processing tools, and we saw that in this case, both types of fiber were able to image the injection interval. And the main difference in this case was, again, the noise floor, which is lower in the engineered fiber. So here's a comparison of the gas and SOV, the permanent source, with a conventional survey, seismic survey. So this line here was actually from one of the surface, 3D surface, seismic with geophones that we acquired on site. So this was processed using 4,000 fiber-size shots and 900 geophones deployed on the surface, while this little line here was acquired using 1 well with gas and 1 SOV source. And you can see that the reflections match quite well with the conventional seismic, also around the injection interval. So the other sample that I want to show is the ADM project. So the ADM is actually a company in the food industry, and they have a biofuel processing plant in Decatur, Illinois. They produce ethanol and they store the CO2 generated from the fermentation process. So they are a large-scale carbon capture facility, and they store more than 1 million tons of CO2 per year. And one of the components of the monitoring there on site is to use DAS and also use these same permanent sources, so 5 permanent sources. So we have here deployed 2 lines, 2 surface lines with fiber. In this cable that we deployed here, we have also the engineered fiber. So we have a combination of telecom fibers and engineered fibers. One different thing here is that the fibers are actually helically wound along the cable axis, and this is done to improve the angle sensitivity of the fiber. So you see the angle sensitivity, as I mentioned, is it's quite strong. It's stronger than the geophones, if you want to put in comparison. And to acquire surface seismic, you want to be able to improve the angle sensitivity. So we actually face a lot of issues with this deployment, with this project generally. One of the issues that we faced, it was just the data transfer from the site to our office in LBNL. The internet bandwidth wasn't very good for that. And as you know, DAS gives these really big data sets, huge data sets. So that was an issue for the project. Another issue that we faced was the data quality. So it turns out that the coupling along the fiber was very variable. Also, the helically wound didn't have the result that we were expecting. So I'll show you some of the results, but this is still a work in progress. So just to illustrate the effects of having engineered fiber and the single mode fiber, this was the installation on site. So here we had single mode fiber spliced into the engineered fiber. And this was just one sweep for the source. So you can see that along the engineered fiber, you actually see the sweep, but on the single mode fiber, you see nothing. So yeah, this is just to illustrate how much we can gain by using engineered fiber, especially for surface, for seismic acquisition. So I tried my best to process this really noisy data set. I tried different things, but once I have tried different noise attenuation techniques, I did see that there were some things that looked like reflection. As I said, the coupling varies a lot along the fiber cable. You can see that here the coupling is not really good. There's basically no continuous reflection here, and the reflections along the whole section, it's not very continuous. But we do see some areas where the coupling is better, and there could be actually reflections from our target interval. So I wanted to compare that with a ray tracing to see if this was actually true. And it turns out that this reflection matches well with the reflection from the field, which is the Eau Claire shale. So I tried to, even using that really noisy data, I tried to migrate this and compare the migrated section with the synthetic seismograms from the well logs on site. And again, this reflection matches with the reflection from the shale, from the cap rock. So this kind of tells us that although the data set is really, really noisy, but we might be in the right direction when it comes to surface seismic acquisition with DAS. So just to conclude, well, we need to be able to monitor for a really long time when it comes to CCS projects, and DAS is a good technology for this. It allows us to permanently store and acquire on-demand seismic data. And in the stage 3 of the Otway project is doing exactly this. So they're trying to build this permanent on-demand seismic acquisition that is meant to reduce footprint and automatically acquire data and process data. So we think that the DAS and also the SOB gives the good alternative for permanent seismic monitoring and gives sufficient signal-to-noise ratio. But when it comes to surface seismic acquisition with gas, it is still challenging due to angle sensitivity patterns, but we might be able to be in the right track if we use engineered fibers to improve the signal-to-noise ratio. And I want to acknowledge all the funding that we received, and thanks for listening.
Great, that was excellent. I think that was a really comprehensive view of continuous monitoring in these two projects. And so we had a couple of questions come through, and I'm sure there's going to be more coming in. The first, kind of along the lines of engineered fiber, could you kind of explain, like there was some discussion of dynamic range or like the higher signal to noise ratio. The question from Menno is, the engineered fiber has a higher signal to noise ratio. And if there is more backscattering, does that mean that the dynamic range decreases for the engineered fiber? Does the dynamic range differ between the engineered fiber and the standard telecom fiber?
So I don't know if I can answer the question. My first answer would be no, it doesn't increase. And we can kind of see that from this plot here. We basically, along the signal range, the frequency spectrum is very similar. So I think, no, it doesn't. The main difference is that it lowers the noise floor. But some people in the audience might be able to answer this, because I know there's some people in the optics in there, in the optics area.
Yeah, I think perhaps there'll be discussion of dynamic range continued in Alexi's talk also.
Yeah.
There's a question about the actual cable that was used at Otway. So was there steel armor to the cable, or what was the kind of jacket composite of the cable? You said it was grouted in, but.
This was, if I understand correctly, the question. So we both used for both. So for the tubing deployment and also for the cemented deployment, it was rubber, cable. So it wasn't. It was just something really simple like that. But yeah.
Yeah.
Yeah,
I think that's the question, is like, is it, the question about like, the different types of jackets allow for maybe picking up different types of tube waves or surface waves. But another question from John Hole about engineered fiber, the rough cost, what's the cost ratio of engineered fiber versus standard fiber?
I think it wouldn't be very right for me to answer this, but actually my experience is that there's a huge range of costs. And, now there are actually a variety of different engineered fibers out there. And some of them that I've seen, it's not that much more expensive than the single mode fibers, or some of these engineered fibers.
Yeah. And thinking about the actual comparison, could you explain how DAS and geophones compare, like how the actual recordings compare, kind of maybe wiggle for wiggle, or the actual how you would compare these two recordings? You did a lot of comparisons kind of in one method.
Right. Well, so in this case here, we integrate the DAS data. So here we have a strain measurement compared to particle velocity measurement. When it comes to, when I was comparing the migrated section, so let's just jump into the migrated section. 1 second.
Yeah, I think the question was actually explicitly on slide 14.
Okay, so when it comes to this section, because we're comparing conventional, we're comparing surface seismic with geophones, with VSP. VSP, you use basically the upgoing waves. So in this case, I actually flipped the polarity of the data, so I'm able to compare with the geophones.
Gotcha. Great. How long is the recording length? And could you detect deeper features in the crust that were not your focus? I think this is in the ADM experiment.
Oh,
how long is
the ADM? Sorry?
The length of the fiber. How long was the fiber?
Oh, okay. So the fiber is actually 13, about a bit over 1 kilometer this side and a bit over 1.5 in this side.
Yeah. Cool. Yeah, I think I think there's a question about maybe aperture and being able to record deeper features in the crust.
Yeah, totally. So yeah, you're right. And this is something that now we see, but I would say that you would have a better chance of acquiring, sensing these deeper reflections if you have a longer offset. However, it is also a kind of it's a difficult spot, because if you go too far, then the gas is not going to sense any reflections anyway. It's just way too far. So it's something that you have to test. Yeah.
And just briefly, in 1 minute, question about data transfer, data at the ADM experiment. How much data were collected, and you described this kind of data transfer issue. So is there a solution that we have yet?
So there was, I think there was about 200 terabytes of data collected so far that we have right now, because we had all these issues. It's not acquiring data anymore. We want to solve a few things before we turn it on again. But the data is not available, but also talking about how data transfer works in the Otway project. So, okay, so the ADM project started in 2017, right? And we learned a lot from them. And now the Otway project just started 2 months ago to record data continuously, and that's 1 terabyte of data acquired every single day. And that we don't have any issues with data transfer, because at this point we realize that a lot of the
Sorry, can participants please mute?
Yeah, so at this point in 2020, we realized that some of the processing should be done on site, and so now we're actually doing all the processing on site, but we saw that the biggest data reduction for the Otway portion, for example, happens until we have all the switch stacks and data and channel stack as well. So, which makes sense, right? Yeah. And we don't have any issues with that.
Yeah, gotcha.
Yeah.
Well, yeah, thank you very much for that great talk and for taking questions.